Okay, so here we discuss partial derivatives, and remember that partial derivatives are only defined for functions of several variables. So sometimes students are a little bit confused between what is a derivative, what is a partial derivative. It's a very simple thing. If there is a single variable, then it's a derivative. If there are several variables, then you define partial derivatives. So here, let's assume we have a function g of two variables, x and y. Right? So in that case, what does that mean? That means that the value of a function, g, is now a function of not just one variable, x, but also of another variable, which we're going to call y. So here is a function. It's a function of two variables, and let's say for any given x naught, y naught, the function gives us the value here. So to any x naught, y naught, we can associate a value of the function j. That would be j at x naught, y naught. And so if we ask the same question as before, so how does the value of the function g, so how does the value of this function here changes as I'm moving around x naught, y naught? Well, you directly see the difference with a function of one variable, because the function may increase or decrease depending on how you move around this point. So here, for instance, if I'm moving along the x-axis, so if I go from an x naught to a x naught plus delta x, then the value of the function is decreasing. But if I am moving along the y-axis here, so if I'm going to a y naught plus a delta y naught, then the value of the function is increasing. And that is why you need partial differential. That's exactly the information which is included into the partial derivatives. So the partial g partial x here, that means that we're holding y fixed, so y is going to be fixed at y naught. This tells you how does the value of g change when we move along the x-axis. So that means when only x changes. So this corresponds here to be moving in this direction, and here the value of the function would decrease. So the partial of g with respect to x would be negative. So another way of describing this partial is to say that this represents the rate of change of g with respect to x, y being fixed. With respect to x, okay, likewise we can define the partial of g with respect to y. This time it's x, which is held fixed at x naught, and this describes how the value of g changes when we only change y. So when only y changes. Right? So this is the rate of change of g with respect to y. So if you wanted to know how g varies, you see that it's not enough to have one number, to have one derivative. You need two. And I say two, you would say you need at least two. It turns out, and this I'm not going to describe here, but if you were moving in any other direction than just x and y, you would know what the derivative is in this direction. That would be called the directional derivative. And you only need to know those two numbers here. If the function is well behaved, you just need to know partial g partial x and partial g partial y to deduce the derivative, the directional derivative, in any other direction. So how does g vary? We need two numbers, partial g partial x and partial g partial y here. So we need two numbers. It's a two-dimensional array. It makes sense to write this as a vector, and that is the gradient vector. So the information which for a function of one variable you have in the derivative, you need more than one number, you need a vector in a function of several variables, and that is the gradient vector. and in IFD I will represent the gradient vector with the nabla sign. So this would be the gradient of the function g. Okay, so in 3D, for a function of several variables, you also have the concept of partial differential. It's also closely linked to the linear approximation. And the idea is very similar to what we had in 1D. Of course, when you look at the function I just plotted here, so this function, this is not a linear function at all, but if you were to zoom really, really close to this point x0, y0, then you would see that the function remains relatively close to a plane. Right? And so the linear approximation simply states that if you are in the neighborhood of this point x0, y0, you can approximate the value of the function, so the function g here in the black curve, by the value of a linear approximation which corresponds to that blue plane. And the difference between the two will be small as long as you remain in the neighborhood of x0, y0. So how do you deduce this linear approximation? Well, you can deduce it directly from a Taylor expansion. And here you're interested in the function, the value of the function g, right? Not exactly at x0, y0, but in the neighborhood of x0, y0. So if we took a random step, small step delta x in the x direction, and a different small step in the y direction. So the value of the function would be close to the value of the function of x, y, y0, but not quite, right? You would have to add partial g, partial x at x0, y0 times delta x plus partial g, partial y at x0, y0 times delta y, plus, if this is an equality, higher order terms will scale with delta x squared, right? And so when you are doing the linear approximation, then you assume that the value of the function in the neighborhood is exactly equal to these three terms, which correspond to the equation of the plane which I drew. So another way of seeing this linear approximation is that this tells you how does g change. So if you take g at x plus delta x and y0 plus delta y minus g at x0, y0, that gives you a change in delta g. How does g change when you take a step delta x in the x direction and a step delta y in the y direction? This is linked to the total differential. And here the total differential of the function g is simply equal, that would be this delta g, to partial g, partial x times the differential dx, plus partial g, partial y, times the differential dy. So if you ask the question, how does the function g changes? So that is, what is delta g for if I take a step delta x in the x direction, and a step delta y in the y direction, then, you know, from the linear approximation or the total differential, what we can write is that delta g, this delta g is going to be equal to partial g, partial x at the point at which we are, times delta x plus partial g, partial y, times delta y. So one way of seeing this is that here the change in the value of g So I'm not sure if I said that again, but what you can see here is that the change of the value of delta g is due partly to a step of delta x, and this quantity here now, the partial g partial x times delta x, will be the change in the value of the function g due to the step of delta x, and here will be the same. This will be the value of the change in g due to the step in delta y, and I can tell the step delta x and this step delta y independently, because g is a function of two independent variable. So I can take that would corresponds to here around this point x naught y naught. I am free to move along the x direction by as much as I want, and by along the y direction as much as I want. I can pick any delta x, delta y as I want.